Okay, so I think probably the most useful thing for you guys is to just go through all the homework problems and work them out and make sure that everybody understands what's going on with them.
Can we start with the ones that were for lecture yesterday?
Yeah.
And then go back to the
And go back, yeah, sure. Okay, so the ones that were from lecture yesterday. So I know 9 is something that we covered in lecture yesterday, which I made you guys something, because I've had trouble explaining this. So I did an art project. Just give me 1 second. So the question is about why don't we have an eclipse every month? You know, so an eclipse, a lunar eclipse, happens when the full moon passes through the Earth's shadow. So that means it happens when the moon is in a line. The moon, the sun, and then the Earth, and then the moon all make a line, right? And so if the Earth is going around the sun and the moon's going around the Earth, how come that doesn't happen every month? And it's because the way that the moon goes around the Earth is tilted from the orbit of the Earth around the sun. So if this pencil here and piece of cereal box is the sun, and then this pencil over here is the Earth, and then this little piece of cereal box here, this is the path, the outside of this is the path that the moon takes around the Earth. So the moon is going around here. And then this string here is the line between the sun and the Earth. So if they were lined up, then every month the moon would go around here and be in a line with this line, right? Every month. But they're not actually lined up. This is tilted like this. So that means that if you're in this part of the year, if you're going around this edge of this cereal box as the moon, you're never going to be in line with this string, right? Do you guys see that? It's either going to be above it or below it. But, I need to put some tape on there, hold that in place. So it's tilted like this, and it's moving around. If it's over here, in this part of the year, then when the moon is right here, it's basically going to be in a line right on that string. Yeah, and if it's right here, you'll get a solar eclipse because the moon's coming in between. And if it's right over here, you'll get a lunar eclipse. But when it's this time of the year, you won't get any eclipses because the moon will be down here or up here.
Does it always happen at that time of the year? It doesn't always happen.
So it'll be this time of the year. So it's only a 5% tilt. So it's really just like this. And so you'll get partial eclipses, like right here in this part of the year, you would get a partial eclipse, where just like the bottom of the moon is on that line, or just the top of the moon right here. You get a partial solar eclipse and a partial lunar eclipse. And then you'd only get a total eclipse when it's in this line.
I know, but like, does that total eclipse that always happens every year at the same? That doesn't always happen every year, right?
Like within the same window?
It's in kind of different. Well, so it's not exactly lined up. Like, so the moon has a 28-day cycle, and the Earth goes around the sun in 365 days, and it's not perfectly divisible. That's why we sometimes have like 2 full moons in a month. So it kind of gets a little bit later or a little bit later every year. Yeah, it slowly shifts, but it'll be, you know, if you have eclipses in one time of year, then the next time of year it'll be just a little bit different. And then the next year it'll be a little bit farther away from that. And the next year it'll be a little farther away from that.
So the answer is because of the tilt.
Right, the orbital plane, the moon's orbital plane is tilted 5% from the orbital plane of the Earth. If you guys want to play with this, feel free to, just to kind of see it yourself. How much this line
really
here?
helpful though. Thank you.
Good. I worked really hard on it.
Like, how can I?
No, we did a lot of this sort of stuff in my dynamics class when we're dealing with 3D orbits, and it's super helpful to have this sort of thing. So I'm just gonna have this up here if you guys want to look at that. So does everybody, does that make sense to you guys? Did you miss that part? Okay, so just real quick, the reason we don't have eclipses every month. So this is the sun, this is the earth, the string is the line between the sun and the earth, and then the moon's going around the outside of this. So if this is tilted, we're not gonna have an eclipse this month. But over here, we're gonna have an eclipse because the moon's gonna hit this string, right? But over here we won't. And then back over on this side, it will have the string on the bottom. It really only works on like one half of it. Okay. So then the other questions from last lesson. So we have 13, which is make a diagram that demonstrates retrograde motion of Mars as seen from Earth. So this is that kind of weird little loop-de-loop that Mars looks like it makes from Earth. So the way that this works is got Earth going around the sun, and you've got Mars going around the sun farther out. So this is where the Earth is, like at certain times. It's gonna be here, and then here, then here, then here, then here, and so on. And then Mars is gonna not, because they're both going around the sun, and this has like a wide, it's got a bigger circle it's got to make, it's not gonna go as far around in the same amount of time. It's gonna go like, so if you're looking in a line from Earth to Mars, sorry, I'm not good at drawing straight lines. Mars looks like it does this. Right?
From our view.
From our view.
Why does like the 6 go down and the 5 and like the 4?
Because if you're looking this line here, from us to Mars in a straight line.
Oh, because the numbers are like.
Right. So this is where Earth is at one point, and then at time 2, Earth is here, Mars is here, and Earth is here, Mars is here, Earth is here, Mars is here, Earth is here, Mars is here.
Yeah.
And time. So at one point you can look from Earth to Mars here. At the next time you're looking there, then there. At this time you're looking up this way. And then if you just connect, okay, first it looks here, then here. So this is like what you see up in the sky as you look
And
from
it
Earth
always
to
does
Mars.
that little loop there.
Mm-hmm.
So you would just set it up just like this?
Yep, you can just draw a picture just like this.
I take a picture of that.
Yeah, of course. You just want to make sure that Earth goes in the same time. Earth is going to cover more of its orbit than Mars does, because it has to go a larger distance, right? You know that circumference.
So would like Jupiter be even more like with the other planets? They would have an even crazier thing.
Yes, so they would have they call these, so back when they thought that the Earth was at the center of the universe and all the planets revolved around Earth, they had some trouble explaining why it looked like this. right? Because it makes sense if everything runs the sun. It makes sense why it looks like that. You know, because they're just going in straight in normal circles. But when they thought that Mars was going around the Earth, it was like, well, why does it look like this? So they thought the planets actually had orbits that looked like this around the Earth. They call these epicycles. And so, yeah, they thought that the planets were all on
Including
epicycles.
the sun. Does the sun also doing that?
So the sun doesn't do that because we are going around the sun.
No, I know, but when they were thinking about it like that.
Right, no, because so this only happens because two things are going around the same object.
Right.
So, like, we are actually going around the sun, and Mars is also going around the sun. So we see Mars like this, but we don't see the sun like this. We see, they saw, and we, you know, you guys know what the sun looks like. It just goes overhead. So they thought that was just the sun going around us. And they thought the sun was the closest into us. Okay? Where did I go? So then 14, which of the following are found in the solar system? So do we have asteroids in the solar system?
Yeah.
Yeah, we know that. We've been hit by them sometimes. Gas giant planets, we have those in the solar system.
Yeah.
Yep, Jupiter, Saturn, Neptune, Uranus, all gas giants. We have comets. Yeah, have you guys ever seen a comet? Sometimes they come around. It's pretty cool. Halley's Comet's not coming around for another, they come like every 76 years. Fun story, Mark Twain was born in a year that Halley's Comet was here, and then he died the next time it showed up.
Wow.
See that? I guess you see
I don't know, but he said, you know, I came in with the comet and I'm going out with it too. And then we have planets in the solar system. Yep, so we have all of those here in the solar system. Okay, so then 17 is one that we went over. Why is there almost no atomic hydrogen or helium in the atmospheres of the inner four planets in the solar system? So do you guys understand, like, did he make clear the concept of escape velocity? Okay, so, you know, like if you have a ball and you throw it up in the air pretty slowly, and it goes up in the air and it gets to a certain height and it comes back down. And then you throw it up faster and it's gonna go up higher, but it's gonna come back down. And then you put like a jet engine on this ball and it's gonna go really fast and it's gonna go up really high and then it's gonna come back down. And next you strap like a Saturn V rocket to this ball. That's like what took them to the moon. So it's gonna go up really, really fast and really, really high, and it's not gonna come back down. So there's a certain speed that you have to go to not come back down, right? And if you go slower than this, then you're gonna fall back down. And if you go faster, then you're going to escape whatever body you're on, so the Earth. And so that's escape velocity.
And it has to do with gravity?
Yes.
And gravity only has to do simply with the size of
The mass of
Mass
the
that
body.
you're on.
So escape velocity, it's based on gravity and then how far away you are from like the center of the body. So the escape velocity from the surface of the Earth is greater than the escape velocity, you know, if you're up in the atmosphere already. But essentially, yes. So like a bigger object, something like Jupiter, would have a much higher escape velocity because it has more mass than the Earth does. So yeah, so it's just the minimum speed that you can go and basically get off into space and not fall back down. So, you know, that gases at certain, you know, how fast they move is dependent on temperature.
So escape velocity is the amount of speed you have to go and then not be able to come back.
Right, to get like out into space and not be trapped on the Earth or whatever planet you're talking about. So, so hydrogen and helium move fast at the temperature of these planets because we're closer to the sun and we're warmer. at that temperature, hydrogen and helium move faster than the escape velocity. So they can make it out of the atmosphere and just go off into space.
Does that have to do with the amount of energy that the isotopes have?
Yes, that energy, temperature is just a measure of energy, essentially. And things that have more energy move faster. So a gas that's at a higher temperature, the molecules are going to be moving faster.
And it's because we're closer to the sun.
Mhm. Yeah, we're closer in, it's hotter in our atmospheres. And so hydrogen and helium move fast enough that they're greater than the escape velocity, and they can make it out into space. Okay.
But then you would reason that like Jupiter and those ones, it's also that they're further away from the sun, but also that they have a larger mass, and so therefore
Right.
a higher escape velocity. So it's both.
Yep.
Are contributing.
It's they can be colder, and they are also have Jupiter's got a huge escape velocity compared to the Earth. Yep. Okay, so is everybody good on that? You guys have any more questions about that? Okay. And escape velocity, I mean, it's really important. We had to figure out what the escape velocity of the Earth to know, how big of a rocket do we need to make to shoot somebody off into space. It has to be able to go faster than the escape velocity, or else they're just going to get up high and then come right back down.
Atomic hydrogen or helium is just like hydrogen and helium. Does that mean something different? Does atomic?
Just, it means it's not not in a water molecule. Like atomic hydrogen is just hydrogen on its own. It's not bound up in like H2O. Okay. So then why is the surface of Venus hotter than the surface of Mercury, even though Mercury is much closer to the sun?
Greenhouse.
The greenhouse effect. Yep. So does that make sense to you guys why that happens? Heat comes in, it gets trapped in the atmosphere, it can't get back out. But Mercury doesn't have an atmosphere, so the heat just kind of comes in, heats up, and goes back out. It's still really hot on Mercury,
Yeah.
but it's hotter on Venus because the heat gets trapped there. So all you really need to put for that question is the greenhouse effect. Okay. You guys feel okay on the stuff that we did last class now? Yes? All right. So then, okay. We can go right ahead and go back up and start with 1. If that's okay, you guys? All right, so if the Earth's spin axis was not tilted with respect to the Earth's orbital plane around the sun, which of the following would be true? So, at the sun, and you got the Earth going around, and it's tilted like this. Right? So, when you're over here, the sunlight's coming this way, and it lights up the half of the Earth that's facing it, right? So this side is dark and nighttime, and this side is daytime. So, but the Earth is turning like this. So if someone is down here in the southern hemisphere, they're going to spend more time in daylight than they are in night. But if you're in the northern hemisphere, you're going to spend more time in night than you are in daylight, right?
Yeah.
And then on the other side, so is this, for the northern hemisphere, is this summer or winter?
Winter.
Right, this is winter. and summer down here. And then on this side, got this side dark. So now someone in the northern hemisphere has a long day and a short night. But in the southern hemisphere, they have a long night and a short day. This is summer up here and winter here. And then when they're like this whole side is away from the sun and the whole other side is in the light. So it doesn't matter if you're in the northern or the southern hemisphere, you're going to spend half the time in dark and half the time in light. Does that make sense?
Yeah, so it's more like fall or spring.
Right. This is fall and spring.
How would that look like? How would that look with like you? Yeah, okay, I get it.
So the sunlight's coming and it's hitting the other side of this circle.
Okay.
Right? Like if,
But aren't all that like half the sunlight's hitting half of that circle too?
right, but it's hitting, right, the sunlight's coming and hitting this half, and then it's hitting all of this circle.
Yeah.
And this half of this circle. So this is like tilted more like this.
Okay.
Right?
Yeah.
So if it's, you know, if this were a circle,
Yeah.
it would be this whole side is getting hit. And then over here, you know, whereas when it's tilted like this, it's half and half. Okay? So that's why you have like, you know, your spring equinox and your fall equinox, the days are exactly 12 hours long and the nights are 12 hours long. But then you have your summer and winter solstices when you have the shortest day and the longest day, or the longest day for summer solstice and shortest day for winter solstice. So throughout the year, the length of the day changes. And you guys know that. You know that in the winter it gets dark earlier. Like you're used to that. So that is, so if the earth were not tilted, then over here, you'd be spending the same amount of time in light as you would in dark. And the same with over there, right? Does that make sense? Okay. So this change in the length of days happens because of the tilt. Right? So you still, if it's not tilted, you still have day and night because it's still turning. Right? And you have day and night because sometimes one part's facing the sun and then the earth turns and it's facing the other part. But the change in how much of that is split up into daylight and nighttime is because of the tilt.
So the answer for
So the number of daylight hours in a day would not change throughout the year if there was no tilt. Is that true or false?
true.
True. Right. You would have the same, you get 12 hours of daylight, 12 hours of night. At this time, the same thing. 12 hours of night, 12 hours of day. Okay, the length of a day would increase from 24 hours to 365 days. False, right. The length matters because that's how much the earth turns. That's how long it takes the earth to go one rotation. The change of seasons will become more pronounced in the northern hemisphere. False. Would we have seasons at all?
No.
Right, it would be the same. You'd have the same amount of sunlight no matter what time of year you were in. And then there would be no change in the pattern of the seasons compared to the real situation. Is that true or false?
False.
Right, there would be a change. It would go to having no seasons. Okay. Does everyone feel good about that? Okay, and you, like on your test, you can draw diagrams like this. Like on your quiz, you can draw things out if that helps you think about them. Okay, next question is, what time does the new moon rise? Draw a picture to demonstrate your answer. I'm just gonna kind of walk you through how I draw these pictures. So you wanna start off, sorry, I'm really short, with the sun up here. And then you've got the earth right here. And this is like a top-down view. So this is like one of the poles. And the earth is turning this way. So we're looking down at the earth, and it's turning underneath us. Okay? So if you are standing right here on the earth, right on this side, what time of day is it for you? Right, it's noon, because if you look straight up ahead of you, you're gonna see the sun, and it's gonna be right overhead. And what about if you're standing right here? Midnight. And what about if you're standing right here? What time is it?
Sunrise.
It's sunrise. Because if you look off to the side, you're gonna see the sun, and you're moving more underneath the sun. And then over here,
Sunset.
right, this is sunset. You look off to the side and you see the sun, just like you do at sunrise or sunset, and you're moving out from under the sun. It's getting darker. Okay, so that's how you do your times of day. Now we're gonna draw our moons. So the sun only lights up half of the moon that's facing it. So if this guy looks up at the moon, what does he see?
No.
Nothing, right? It's just black. So what type of moon is that? New moon. What's this guy gonna see? A full moon. And then this guy is gonna see a half moon. And this guy's also gonna see a half moon.
Would it be flip? Oh no, it's the okay.
Yeah. So the moon rotates in the same direction that the Earth does. This is a first quarter moon. This is a third quarter. Okay, so this moon going around, this happens on a 28-day cycle. It takes 28 days to go from here all the way around. But it only takes 1 day to go around here. So then you want to pick what moon phase you're talking about. So in this question, I think it's the new moon. So you're going to pick the new moon and you're going to hold the moon still and just ignore all your other moons. And then you're going to turn the Earth underneath it. So you're just looking at this part. And you want to ask yourself, okay, so where of these do I have to stand so this moon is rising?
On sunrise.
At sunrise. You're going to stand there. The moon is going to be to the side. And you're moving more underneath it. So it's going to get higher in your sky. So the new moon rises at sunrise. It's directly overhead at noon. And it sets at sunset. What time does the full moon rise?
And sunset.
At sunset, right? You ignore all the other ones. You say, okay, it's going to be right over to the side. And I'm moving more underneath it. Okay? So you can draw a diagram just like this.
So that
Are we expected to know the other crescents that the moon's in?
I think all that is really, I think it would just be confined to these four.
Gotcha.
So the other ones would be, you know, you've got your crescent here, this is your waxing crescent, this is your waxing gibbous. That's like the,
So the answer is sunrise.
yeah, sunrise is gonna be your answer. This is your waning gibbous and your waning crescent, but I think just full your waxing or first quarter, new moon, and your waning or third quarter is all you should be need to know. These guys are, you know, this is noon, sunset, midnight, sunrise. This is about, you know, 9 a.m.
So
noon, 3
Is the
p.m.
answer is it sunrise or like an exact time? Like
You just have to put sunrise,
Okay.
because sunrise isn't always the same time, depending on what time of year you are. But it's, yeah, you just have to put sunrise. This is like this 9 a.m. to 3 p.m. is really approximate. Yeah, so all you should have to really worry about is this part. You can draw this diagram, then you should be able to answer any questions. Okay. So then 3 is given that the speed of light, c, is equal to 300,000 kilometers per second. How many miles are there in a light minute? So I don't know how many of you guys were here in past sections of mine where I kind of go over the way I do unit conversions. So I'll kind of briefly review that for this problem. I set them all up in this grid. So you start out with what you have and you put it in the first grid. You have 300,000 kilometers. If you have a unit like kilometers per second, you put the top one in the top grid and the bottom unit in the second one. So this is 1 second. And then you take your conversion factor. So we have 1 kilometer is 0.62 miles. And then whatever you have up in the top grid, you're gonna put in a bottom square now. So they make a cross from each other. So we're putting 1 kilometer down here and 0.62 miles up here. You take your conversion factor, you split it up, 1 on top, 1 on bottom. Whatever's in the top over here, you're putting in the bottom over here. And then we have 60 seconds is 1 minute. So now we have seconds on bottom. We're gonna put them on top over here. 60 seconds and 1 minute on bottom. And then now you can kind of, for units, you can cross them out, like if one's on top and one's on bottom, just like you would do for like cross multiplication. Kilometers, kilometers, seconds, seconds. So the units that we're left with are miles per minute, which is what we're looking for in this question. And you multiply across the top and divide across the bottom. So we have 300,000 times 0.62 times 60 divided by 1, divided by 1, divided by 1. And that gives us,
that conversion from kilometers to miles.
that is
No.
something that would be like given.
Okay.
I don't think you'd be expected to know that. And so it's 11,160,000 miles in a minute. And I wrote up some extra math practice problems for you guys, some unit conversions like this. I gave him some mic to put on the website since I don't have access to the email list. So hopefully he'll put them up on the class website. I put my solutions that are all worked out and everything. So if you just want to see some more examples, hopefully those will be up on there. You can try some yourself and can see the way that I did them.
Without a calculator, are we expected to know how to use like Planck's constant and Wien's law?
Anything that's going to be on there is going to be really easily calculable. Like it'll be multiples of 2 or all you have to do is like divide by 2 or maybe divide by 5 or something.
So you probably won't use what Wien's law because it's got a
0.29.
yeah.
I don't know, but there won't be any. There's not going to be anything that is not, maybe it'll be something you have to do. You have to divide by 10 or divide by 100 or something, something that you guys can do pretty simply.
True.
Okay. All right, does everyone feel comfortable with this one? Okay, the next question, suppose you live on the moon where there's essentially no atmosphere. And then we're going to say label the following statements as true or false. Get my colored markers here. Oh no. I don't know where they are. I must have left them in another classroom. That's a bummer. Okay, well. Damn. Okay. So we've got the sun up here. And it's giving off light in all sorts of wavelengths. And it's white light, so it's made up of all different colors, including blue. So that's blue, and say, this is red, yellow, green, orange, so on and so on. And it hits the atmosphere. And the blue gets scattered. So the blue starts going all sorts of ways. And then everything else just comes down in a line. So if we are down here, one person with our eye, it's like an eye from the side, so it's looking up that way. That's this symbol. It's looking this way. If we look anywhere but directly at the sun, all we're going to see is blue, right? That's all it's coming down at us. And if we look right at the sun, we're going to see white light minus blue. So it's going to look like more red than it does normally, right? But if there's no atmosphere, then everything just comes, including the blue, is just coming straight down to your eye because it's not getting scattered. So if there's no atmosphere, is the sun gonna look more red? No, right. It's gonna look more blue, which in this case is white. But it's definitely not gonna look more red. So the answer to this first part, the sun will appear redder as compared to seen from Earth during the day. That's false. It's gonna look more blue or more like white.
Why what is, or yellow and green just don't do that. It would look green.
No, well, so if the atmosphere were the right atmosphere to scatter green, then we would have a green sky.
But red is more dominant, that's why it looks more red, right?
Red and blue are kind of like the
They're
ends
the shortest
of the
longest.
spectrum. And so when we say something is like more red, it just means it's more towards that end of the visible spectrum, and more blue is more towards that end of the visible spectrum. So the other colors are kind of in between. So like green is more red than blue is, because it's more towards the red end than blue is, right? And green is more blue than red is. Okay? So then the color of the sky looking away from the sun during the day would be black. You look away from the sun, what do you see? No light, so it's black. So that's true. At sunset on the moon, the sun would appear redder than it does at noon. So on Earth, so there's still a little bit of blue that comes down with the sun that doesn't get scattered, like at noon. This only takes away so much of it. But the more atmosphere that you go through, the less blue is here. So on the Earth, you got the Earth, and then you've got our atmosphere, right? So at noon, the sun is over here, directly overhead. And these waves have to go through this much atmosphere to get to a person. At sunset, with the sun over here, it has to go through this much atmosphere to get to a person. So that's more atmosphere, which means it takes more blue away, which means the sun looks more red at sunset, right? Because there's less blue, so more red. If there's no atmosphere at all, is that going to happen? Right. So is the sun going to look even more red on the moon? It's going to look the same color, right? It's going through this, if there's no atmosphere at all, it's going through the same amount of atmosphere if it's at noon or if it's at sunset, and that's no atmosphere, none atmosphere. Okay?
So how would it would look better? Or no, it would look better.
So it looks, on the Earth, it looks redder than it does at noon because it's going through more atmosphere. So at sunset, so that more atmosphere makes it look redder. At sunset on the moon, is it going through more atmosphere than it does on the Earth? Right, it's not going through any atmosphere at all. So is it going to look more red than the Earth? It's going to look just like it always does, which is all the colors, so more blue. Oh, but this is even just at noon. Like, you know, if you're on the moon, leave that guy over here. At noon, goes through no atmosphere, and at sunset, goes through no atmosphere. So there's no difference in how it looks at sunset or at noon, because it's going through the same amount of no atmosphere. Okay, and so then the last part is about the green flash. So the green flash happens, oh, I do a green marker, that's good. Okay. So the atmosphere acts like a prism. You guys have all seen, like, you know, the Pink Floyd cover or whatever, where the white light is coming through this way and then it gets split up into all the different colors of the rainbow, right? So this is, so one of these colors is green. That's nice. So the atmosphere does the same thing. It takes this white light from the sun, and if you go through enough atmosphere, it's gonna split it up and make it look like there's kind of 3 images of the sun. The blue is scattered like this way at this point. It's scattered off, so if you're sitting over here, you don't see it anymore. But you will see a green sun, you know, and like an orange one, and a yellow one. Or a red one. So if you're on the moon and there's no atmosphere, is this happening? Right. So is there going to be a green flash on the moon? Is there going to be a red flash on the moon? Is there going to be any flash on the moon? Nope. It just all goes down at once. So the green flash would be red flash. That is false. There's no flash at all.
What exactly would you see? Just like the sun.
It would just set and not change color. Yeah, it would just kind of go down and it would be the same color as it was at noon. You get this kind of whitish yellow looking sun. It just goes down and it looks exactly the same. So there's a couple of scientific notation ones we can do real quick. Start off, we got 1,000. So to turn it into scientific notation, you take your decimal point and count how many spaces it takes to move till there's just 1 digit in front of the decimal point. So we're counting 1, 2, 3. We get 1 times 10 to the 3 is equal to 1 E3. We have 0.02. I'm going 1, 2. But since we went to the right, we went from a small number to scientific notation. This is a -2. Okay, big number, positive number, small number, really small number, negative number. 1/2 is equal to 0.5. Moving it over to 1. 5 times 10 to -1. Both of these notations are totally fine. I use the E because I get tired of writing times 10 to the, but you can use either. And then we have 300,000. We're going 1, 2, 3, 4, 5, 3 times 10 to the 5. Okay, you guys feel comfortable with these? Okay. Humans have been present for approximately what fraction of the Earth's history? Do you guys remember in class we had this, he showed a calendar basically, and it was like, okay, if you could condense the history of the Earth, yeah, into this calendar. Do you guys remember where humans show up?
The last second.
Yeah, like right at the end. So have we been here for 90%? Nope. 50%? Definitely not. So then you're left with like 1% and a tiny fraction, less than 0.1%. So if all you remember was that we show up on the last day, and you don't remember what time on the last day, but you know we show up sometime on the last day, like how, if we took up the whole last day, what fraction would that be?
Of all of time.
Of all of the Earth's history.
Very small.
Right, but like, so if we show up on the last day of the year, we've been here for 1/365th of the time, right? Because there are 365 days in a year. And you know that 1/365 is going to be less than 1%. So even if you only remember that we show up on the last day, you can do process of elimination and get rid of all of the other ones, and you're left with a tiny fraction, less than 0.001%. Okay. What are the primary advantages of using telescopes? I don't think this has really gone over in class well enough, so I'm just gonna kind of talk about them. So telescopes, we can make them big. Your eye is really small, and that means that we can gather more light in the same amount of time as you can with your eye. So they have more light per unit time than the unaided eye. Another thing that's super useful is that you can increase the magnification. Now you can, with a telescope, you can make something that's really small look really big. That's super helpful. With a telescope, you can look at something for a longer time than you can with your eye. If you're just staring at something, especially a light, your eye's gonna get tired, you're gonna start blinking, it's hard to focus, it's gonna start wandering. And with the telescope, you can just say, look at this thing, and it's gonna keep looking at it until you tell it to stop. So there's a longer, it's called integration time, but you can just think of it, you can look at the same thing for longer. There's something called the diffraction limit. And the idea behind the diffraction limit is, if there's like two trees or two something that you're looking at and they're far away, it's really hard to kind of tell them apart. They kind of just blend into one object, right?
Yeah.
So that happens because it's just diffraction. The diffraction limit is how far apart two objects have to be for us to be able to tell that it's two separate objects. And with a telescope, you can have two objects be a lot closer to each other and be able to tell that it's two separate things than with your eye. So a telescope has a finer diffraction limit. So two objects can be a lot closer together and we can tell them apart than with our eye. So sometimes you'll see something with your eye and it looks like one really bright star. And then you look at it with a telescope and it's really like 7 stars all together. But with our eye, it just looks like one. They all blend together. With a telescope, the diffraction limit, things can be closer together and it can still tell them apart.
So the telescope has like a better, like a farther diffraction limit?
So it's actually a smaller diffraction limit because things can be closer together. So the distance is smaller that they have to be. So you can say finer diffraction limit or smaller diffraction limit. And then another thing is that, so remember in class we showed like the full electromagnetic spectrum. And you had, gamma rays down here all the way over to radio waves. And you remember how much of this we could see just with our eyes? Right. Visible light is like just this little slice of it. And everything else just goes by and we can't see it. But with a telescope, you can see a different type of telescope. You have to use different types of telescopes to see this and this. The telescopes, you can see parts of the spectrum that you can't see with your eye. If you guys have ever seen those really big things that look like a really big antenna, like in like the movie Contact or something, that's a radio telescope. They're huge. Radio waves are really long. They have these long wavelengths. So you use something like this and you can see radio waves. Okay. And, a lot of times when we're looking for signs of like intelligence from outer space, we're looking at radio waves.
Did they like pick up a signal from something like really far away a long time ago?
Mhm.
They got like some weird alien radio.
We could, I mean, if they had put out a wave long enough ago, then yeah, we might be able to detect it. If we're looking in the right spot. That's the problem. There's a really big sky, you know, and so we'd have to be looking in the right spot. So that's why they have these kind of big, you'll see like sometimes when they have these, they have a ton of them kind of in a grid so they can look at more area. Okay. Day and night on Earth are due to, we went over this earlier, not the length of day and night, but the fact that they happen at all is because the spin. So the tilt is how long, like the tilt is how much of that 24 hours is separated into daylight and nighttime. And the seasons are the tilt. But the fact that we have daytime and nighttime at all is the spin, right? So the tilt, and then we're spinning, and that causes daytime and nighttime. Okay. And then why is, so we went over the lunar eclipse one. You guys feel good about that? Okay, what do radio waves and visible electromagnetic radiation have in common, and what properties do they differ? So, what do they have in common?
All light travels at the same speed.
Right. They all travel at the speed of light. They're both types of light, so they both have the same speed. And no matter what type of light it is, it travels at the speed of light.
Does all light technically have a color? It's just
Right.
outside of the range of which
Right.
we can see.
So radio is like a color, basically. Like, because even within that visible light, you've got it spread out into the colors.
Right.
So in the same way that like each color is a specific like range of wavelengths, radio and like ultraviolet is like a color. And so, you know, ultraviolet is past violet,
Right.
infrared, past red on the other side. Yeah.
Yeah.
You can think of radio and that as their color, but we can't see those colors.
Right.
Yeah. So then what do they have differently? So when we look at this spectrum from gamma to radio, invisible light in here, what are we kind of measuring? What are we separating them by?
Wavelength.
Wavelength, right. Radio's got these long wavelengths. Gamma has these short wavelengths. And then sort of the opposite of wavelength, not necessarily the opposite, but what's the other? Frequency, right. So the equation is frequency times wavelength. This lambda is the symbol for wavelength, is equal to speed. So in that case, this is c. So if this stays the same, if this is constant, and you increase your wavelength, and your frequency decreases, right? If one goes up, one has to go down
For CP.
for this to be constant. You know, if this can change, then you can have something that has a high frequency and a high wavelength. It would just be moving faster than the speed of light, which you can't have. Well, I mean, yeah, but
Is frequency like how close the waves are to each other?
so that's more like wavelength. So wavelength is
Is frequency how often they peak?
yes.
Yeah.
So if you got wavelength is like this distance, how far apart the peaks are. So this has a longer wavelength than this does. But if someone were standing right here and they count for like 1 minute and they count how many peaks go past them, that's frequency. So if these two waves are moving at the same speed, this guy's gonna have less peaks go past than this guy, right? So this has got a higher frequency. Right, if he stands here, if he's standing here watching, this one's only gonna have them go by so often, and this one's gonna have them go by a lot faster. We're gonna count 1 wave, 2 wave, 3 waves.
That symbol, is that speed? Or wait, what is that symbol there?
Wavelength.
Lambda, this is wavelength.
Okay.
Yeah. So this is also used in Wien's law. So this is something that you guys should remember. He did say that he was going to give you equations that you need. So, like if there is a question on Wien's, if there is one, then he'll give you that equation.
And then on this also, the shorter the wavelength, the more energy.
Right. Yes, the higher the frequency or the shorter the wavelength, the more energy.
Which has to do with heat. Not necessarily.
Not for light.
Okay.
For other things.
Okay.
So light doesn't really have, light heats things up, but doesn't really have like heat of its own. Heat is like a property of matter.
Okay.
And light's not really matter. It doesn't have mass.
So the wavelengths themselves don't have heat, but they create heat in other objects.
Things, yes. Yeah. And then things, they can make things move faster, or things can move faster by like hitting each other.
So when the sun's touching your skin, it's not the sun that's giving you the heat necessarily, it's the way it interacts with your skin.
Right. The light from the sun makes your skin heat up, but it's not like that the light itself is hot. It's just interacting with your skin
Yeah.
and it's making your skin and heat, and we perceive that as heat. Okay, so you guys good on that one? So the speed of light is the same for all electromagnetic waves, and they have a different wavelength and a different frequency. And they have to balance out. If your frequency goes up, your wavelength goes down. If your wavelength goes down, your frequency goes up. Okay. And then, what color is a yellow banana slug illuminated with blue light? I think it's a green banana slug today. I only have green and blue. So you got your green banana slug here. So he is green because you've got all sorts of colors of light coming this way, including green light. So when there's white light, it's all the colors, including green. And he absorbs everything except for green, which he bounces back off or reflects. So over here, we're looking at this banana slug. We see this green light that he's reflecting. But if there's no green light coming in, he has nothing to bounce off and nothing to reflect. So what do we see when we look at him?
Black.
Right, we don't see any light, which is black.
Just because he absorbs all of the
He
available
absorbs
light.
everything except for green. Yep. And the only one that he bounces off back at us is green. If there's no green coming in, there's no green coming back at us. Okay. Okay, so consider a 1 meter radius copper sphere heated to 100 C and a 1 meter radius clay sphere painted black heated to 100 C. I'm going to label the following. So I'm just going to go over some of this real quick, as fast as I can. So in this class, so far, at least, I'm not totally sure how we'll go for the rest of it, but so far, when we're talking about hot things, you want to kind of separate them into two different categories: hot gases and black bodies, or hot gases and everything else. And we're going to assume that everything else, these black bodies, make these Planck spectra. When you measure the light coming off them, it looks like this. This is intensity. And this is wavelength. So they're giving off, like this guy's giving off light in every color. But there's one color that he's giving off the most light in. So it's gonna look that color because it's got the most, everything else kind of cancels out to white. And then there's extra of that color. So it looks like that color, right? But how exactly this spectrum looks is based on temperature. So if this is a black body at, say, 1,000 Kelvin, the same thing would look like this at 100 Kelvin. So it's the same basic shape, but it's giving off less overall, and it's got a different peak, right? So, if this guy looks blue and this guy looks yellow, this guy's still giving off more blue light or more yellow light than this one is, right? There's more yellow light than this one, but this guy looks more yellow because he has more extra yellow light than all the other colors. And then if it's at, 10K, it's gonna look like this, and it's gonna look, red. This is not really what they look like at 100, but this is just to show, as it gets cooler, the peak wavelength gets longer.
Peak wavelength gets longer.
Yeah.
Will you show that?
So just, like if you look, this is the peak wavelength here. This is the peak wavelength here. This is the peak wavelength here.
You said as it gets cooler, it gets longer.
Yeah, so as this is a hotter object than this, right? This isn't.
No, I still don't understand. I don't see that.
Those things get shorter.
Yeah.
Like the lines get shorter.
Oh, I mean, like if you're measuring wavelength along here.
Okay. Is there a way for us to see that in that though?
Well, so like this is the axis. This axis is wavelength. So this over here, like blue has a shorter wavelength than yellow than red. Like the actual length, the measurement of the wavelength. This line is just to show you where it is. The height of this is the intensity. I'm just pointing out here, here, and here.
It's longer from from zero?
Yes. Like
Okay.
if this is 0.
Okay, so that's
And this is, like this axis is
So-
wavelength.
from
and
0
this
to
is-
B, from 0 to Y, from 0 to R.
Right.
The
This is
cooler, it gets longer.
this is
Got
the
it.
wavelength.
Yes,
this
yes,
is the
yes,
wavelength.
yes.
Yeah. This is intensity. But I'm just showing you this is the peak. And this is where
Got
it
it.
falls.
It's just the bottom part that
Yeah.
I wasn't.
And wavelength is getting longer as you go this way,
Yes.
right? So this is
As is measured by the peak.
right. the peak wavelength is getting longer as you go this way. And as you get a cooler object has a longer peak wavelength than a hotter object. Okay? So, but there's nothing in this graph about what the material is made of, because it doesn't matter as long as it's not a hot gas. You know, we're just dealing with stuff that's not hot gases. It doesn't matter what it's made of,
As long as it's the same.
as long as it's the same temperature. The only thing that matters about which curve it's going to be is temperature. Okay? And this type of spectrum, this Planck spectrum, so it's a smooth curve, so it's called a continuous spectrum. Right, there's no like sharp peaks or sharp dips. Okay, it's a smooth curve. So then looking at these questions, so 1 meter radius copper sphere and a 1 meter radius clay sphere, are either of those hot gases? Nope, so they are both, we're gonna think of them both as these black bodies that make these Planck spectrums. And they are both heated to 100 C, so they are the same temperature. So the copper sphere will produce radiation at shorter wavelengths. False. The copper sphere will produce more total electromagnetic radiation. False. The spheres will produce an electromagnetic spectrum that is identical.
True.
True. They are at the same temperature. That's the only thing that matters. So they will produce an identical spectrum. The copper sphere will produce a distinctive emission line spectrum. False. It is a continuous spectrum. They will both make a continuous spectrum. So hot gases are different, and we'll go over that in a minute. You guys feel okay with this? Okay. Okay, so yeah, so the last two were actually on emission line spectrum. So now we're going to talk about the other thing, which is hot gases. So electrons, or an atom, you've got a nucleus in the center, and then you've got electrons going around. And the electrons have these orbits. And they can only be in these very specific orbits. It can't be going around in here. It has to be going around in here. And it takes a specific amount of energy for it to jump from here to here, or from here to here. And that energy can come from light. So we talked about photons, which is basically just a little piece of light. So if you got, and each different color has a different energy, right? It's got a different wavelength and different frequency, which means a different energy.
And does that literally correspond to like photons with higher energy or photons that are lower in length on the spectrum?
Yeah, so like a gamma ray, like if we're looking at the full spectrum, gamma rays are over here and radio are over here. Gamma rays are much higher energy than radio waves are.
So a gamma, but does that correspond to, if it's correct, like jumping 2 or 3?
Yeah. So like if it's the right thing, like a gamma ray would jump 3 levels, and a radio wave would jump like 1. Okay. Yeah. So, say it takes, so blue is higher energy than green. So say it takes like green amount of energy to go from here to here, and blue amount to go from here to here. And you've got photons coming in that are green and blue, and also sorts of other colors. You can have a red one and a yellow one. So it's coming in, and this electron down here snatches up this green one, and it absorbs it, and it jumps up to this energy level. And this one over here takes this blue one, and it grabs it and takes its energy, and it jumps up to this energy level. So this blue and this green, they get absorbed into here, and the red and the yellow go out. The way that I kind of makes it easier for me to think about is, instead of thinking about it in these kind of rings, is to think about it as like steps. So if you're standing down here, you need a certain amount of energy to be able to jump up to this step, right? And if there is something, you know, maybe this light is like, you know, different colors of energy drink, and they all have different amounts of caffeine in them, right? If there's different ones coming by you, and you grab one and drink it that has just the right amount of energy, you can jump up here. If you get one that doesn't have enough energy, then you're just gonna bounce right back. So you're not gonna bother grabbing it. If you get one that has this much energy, you're gonna hit this wall and fall right back. So you're not gonna bother grabbing it. The only ones you're gonna bother grabbing that are coming at you to drink are the ones that have this much and this much energy, right? The other ones you're gonna let just go right past you and go right through you and keep on their way. So, you know, you could say this one, so you need a green monster to jump up here and a blue one to jump up here, right? So then once you, say, ate this green one and it gave you the energy, and now you're up here, now you're like, oh man, I feel really dizzy, it's high up, I'm getting nauseous, I think I'm gonna puke. And so you do. And you puke and you fall back off and you fall back down here. What color is your puke?
Green.
It's green, right? Because that's what you drank to get up there. So you're gonna, but you don't spit it back off that way. It kind of falls down this way. So you've got a green coming back out in a different direction, right? And each different type of atom.
Are those photon, are the, like, aren't there ones that try to go towards the center? Because you showed the arrows coming away from the center.
No, nothing
No.
wants to go towards the center. Everything wants to move outwards from the
Of
center.
the light, the electron wants to go back towards the center.
It wants to go, yeah,
Which
so
is
that's,
falling
it
down.
wants to go not towards the nucleus, but towards the lowest circle
The
that it can
base.
be in.
The biggest circle.
The smallest circle. It wants to be in the smallest circle. And that's what throwing one back up and going back down and emitting something out. But you can emit it in a different direction. You know, if, shouldn't have erased it. If you've got these circles and the light's coming from this direction, and this electron here gets the right amount of light and it jumps to here, and, you know, say it gets, it gets some blue light and it jumps up to here, and all the other colors go straight through. Then later on, it's gonna, you know, get sick or whatever. It's tired of being up in this one. And it's gonna jump back down to the original one, and it's gonna get rid of that blue light, but it's gonna get it in a different direction.
Always or sometimes in the same direction?
It's basically in a random direction.
Okay.
So it could be in the same direction, but it's, you know, it's totally random, essentially, which direction it goes in. So it's most likely gonna be in a different direction. So different types of, like different types of atoms have different heights of steps. So you can have one that has like this height and one that has this height. So this guy over here needs a different color to jump up to this level or to this level than this guy needs to jump to this level or this level, right? Does that make sense? So this guy's gonna absorb and then spit back out different colors than this one will. So if this is, you know, hydrogen, this is helium.
They always release all of the photons at the same time.
No, but this is happening like, this happens when you have like a big cloud of them. So there's always different molecules, like different atoms that are absorbing and releasing photons and absorbing and releasing photons and absorbing and releasing photons. And we just see sort of the aggregate that's coming out. Okay, so this that we see, this thing that's being spit out, that's like what we see from this hot gas, from this big cloud of these. We see a bunch of this light that gets spit out at us.
So that would be the emission lines.
Right. So when you're talking about the spectrum of a hot gas, it just looks like something like this. You know, and this is green. And this is blue. Oh, yeah, you're right. I'm used to it. We switch wavelengths a lot for HR diagrams. It's weird. Yeah.
X and Y is the same. Like, is that, like, are those two graphs, so are they similar? And that's intensity and wavelength? It's totally different.
It can really depend. Like, depends on the energy levels, because like, and how much is in this light that's coming in. If this light has a lot more blue light, then a lot more blue are going to get absorbed and spit back out than green. Or if some transitions are easier than others.
But as far as the axis of these, is it intensity?
This is again intensity and wavelength. Right, so when we look at this gas, all we see is these two colors. And it's not putting out light in any of the other colors. It's only putting out this amount of light, these two colors. But if it were a different element, then it would be absorbing. You know, this one absorbs green and blue, and this one takes in red and yellow. Right, and so this one spits out red and yellow, and this one spits out green and blue.
And that's why he was saying yesterday that it matters, the elemental makeup of like whatever's happening in the sky matters with the colors of the northern.
Yeah,
light.
That's why you get, like, you don't just get green in the northern light. You'll get some pinks, you'll get some blues, because it, the different particles that are in the atmosphere will put off different colors. Okay, so then this question is, the emission line spectrum of each element shows a unique pattern of wavelengths. Which of the following statements best states the underlying reason for that? What is the reason? Is it because they have a unique atomic weight? Is it because they have different allowed orbital levels?
Yep.
Right, that's the different steps that it can be on. Okay, and then a hot gas emits what type of spectrum? Emission line spectrum. Okay, so if we were over here we would see everything but those two. But that's only if you're right in this line, if you're here, or if you're here, or anywhere else. So we don't really think about that. We just think about what you see if you're looking from any direction. Okay. Oh, I gotta plug my computer in. All right, and that's all the problems on the thing. Do you guys have any more questions? Okay.
I can have a quick question. So, when you're looking at this diagram over here to the left, you could essentially think of each distance from one to the other as a particular color or as corresponding to a particular color
Right.
or wavelength. And that more specifically correlates to the answer of the question.
Right.
Okay. Got it.
And their goal, the whole goal is to get to the lowest level, right?
Yeah.
And the lowest level is the
Yes, the smallest ring is the lowest level. That's not, so they don't really have a goal in, the sense. They just, if something comes by that's the right one, they're gonna grab it. They don't really have a choice about it.
and then
But yeah, they want to go back to
Like
the lowest level.
and then
Natural properties is that
Yes.
it'll always
Yeah.
revert back.
in their attempt to get to the lower level, they let off that other.
Mhm. Yep. Okay.
You know that is the quiz only based on like the homework? Or is it
Yeah,
just
if
based on
you-
overall?
If you can do all the problems on the homework and you understand them all, then you'll be fine on the quiz.
But it's like not gonna be the exact question. It's gonna essentially be variations of them, proving that we understand the concepts, yeah. Cool.
And he's gonna give us